Thanks for joining today to another View of Water Ameriflex webinar. Today it will be all about land-atmosphere interactions, and we will talk a little bit about the observational side, but we also have some modeling content today. And yeah, so our idea behind this webinar is really to link the atmospheric boundary layer that mediates the interactions at the surface with what's happening in the free troposphere to some work that we're currently doing at Ameriflex at the Flux Tower sites, where we're really interested in ecosystem fluxes. But yeah, we hope to here really extend the scale a little bit up to the atmospheric boundary layer scale, where we are then more in the 1 to 3 kilometers above the ground. And we will cover a few different topics today in 4 different talks. So the first talk will be Juliet Pilewskie and Susanne Wiesner from University of Wisconsin-Madison. And then we'll have another talk by Adam Young that will be a live or streaming of his recorded talk today. But I think he will be here for the Q&A session. And then Ryann Wakefield will talk about mixed layer diagrams. And then in the end, Yunyan will wrap it up with some more modeling focused work. Yunyan Zhang will have the last talk of this webinar, and then we will have half an hour of time for Q&A. You can ask all sorts of questions to the presenters. So what I encourage you to do, and we'll drop this link into the chat later on. You can either post your questions here, and I encourage you to add to your question, add name of presenters, so that we can kind of sort out who this is addressed to. Obviously, all the other presenters in the end are happy to respond to these questions too. But yeah, if you have a specific question, add the name of presenter. And then there will be also an option to up and downvote questions. If you would rather just post your questions here in the chat, we'll also have a look at the chat so they won't get lost there. So please feel free to also post your questions there, and then we'll have half an hour time at the end for this discussion. And before we start, I would like to highlight that there is also currently a special issue on land-atmosphere interactions, integrating surface flux and atmospheric boundary layer measurements. So very relevant for this webinar here too, edited by a few of us, you see down here. So I think we have currently 2 published papers, so we are really looking for more submissions. If you have any questions, if your work is relevant for this special issue, you can send an email to me or to any of the guest editors that are listed here, and we're happy to answer all your questions. And now, without further ado, I would give the mic to Juliet and Susie, and they will talk a little bit about boundary layer measurements with balloon soundings. I will stop sharing my screen and mute myself. So they can't unmute themselves. Wait, ask to.
Thanks. Yeah, it didn't allow us, so hopefully now it's fine. Oh, and we also need permissions to share our screen. Sorry.
You may share the screen right now.
Thank you. All right.
All right, well, so thank you very much for having us here to talk. My name is Juliet Pilewskie. I'm a PhD student at University of Wisconsin in Madison.
And my name is Susie Wiesner, and I'm a postdoc at UW-Madison.
And the focus of our presentation today is to ask the question, can we quantify eddy covariance footprint variability and source area characteristics using radiosondes? There we go. Okay. So 3 years ago, Susie and I were involved with a meteorological measurements course through UW-Madison's Department of Atmospheric and Oceanic Science with fellow undergrad and graduate students. The data that is used for today's presentation is from that field course. And so I would like to give a special thanks to my fellow peers, Sophie Hoffman, Peter Jansen, James Minot, Amanda Nassif, and Jess Turner, who took part in gathering that data. And also thank you to Brian Butterworth and Ankur Desai for their help during that experiment. That was my first time being involved in a field campaign, and I learned quite a lot. Okay, so the field course took part in Cheesehead, the IOP1, and so we went up to the Schwamigan-Nicollet National Forest for a week to take measurements. And our experiment addressed the field campaign's aims, which were to understand how the heterogeneity of the vegetation influences surface fluxes. And it's really neat because that forest was highly heterogeneous. And so the experiment design was designed to monitor the surface latent and turbulent fluxes using a cluster of flux towers in the different vegetated regions. So during the 1 week long field experiment or the field course, the undergrad field course, part of our project was to calculate CO2 fluxes, surface fluxes. So we launched winsones for determining the boundary layer to calculate these fluxes. And so the figure on the right shows that we obtained the boundary layer height by identifying a steep increase in potential temperature with altitude. And so these two plots show that over just the course of an hour in the morning, the boundary layer height increased by about 50 meters. So that was really interesting that we could detect that just from 2 different launchings of winsones. And so winsones were used for this calculation because they provide a convenient way for measuring the boundary layer height, as they are cheap and easily recoverable for the most part. I believe we might have only lost 1 or 2 over the 15 or so that we launched, so not too bad at least. And they also provide a Lagrangian perspective for monitoring the local environment. And so Susie and I were curious, how could we fully utilize all of the measurements from the winsones? So this map here shows that the winsones passed over or went near at least 1 or 2 flux towers for what we consider days 2 through 5 of the field, the 1 week long field experiment. And so highlighted in the red are just the flux towers that we essentially looked at that were very close to the windsonde passover, I suppose. And on the left are the calculated boundary layer heights from the windsondes. And we checked them against the wind profiling radar moments that were taken at boundary layer calculations from wind profiler radar moments taken at 2 different sites during the field campaign. And so since we had, sorry, just to go back a little bit. Since we had these boundary layer heights over the flux tower regions, we figured we could use them to improve estimates of flux tower footprints. And so footprint models, what they do are they determine the surface source area, position, and size contribution to the measured fluxes around the flux towers. And so we hypothesized that by adding the information from the specific boundary layer heights from the windsondes, we could improve upon estimates of the footprints, and this with the goal being that we could then upscale or that the footprints could be upscaled from single site flux measurements to local or regional scales. And this is important for eddy covariance fluxes or eddy covariance measurements, pardon me. And so we set up an experiment and created footprints at each of the towers that the sondes passed over, using 3 different experimental setups. And this was we generated these footprints using UMAP QGIS. And so the first experiment was creating a footprint using the Corman and Wiesner model from 2001. And there's no boundary layer implemented in using this model. And then the next experiment or model setup was with the Kiljoen et al. 2015 model with an assumed boundary layer height of 1,500 meters. And then the third was the same Kiljoen et al. 2015 model with the windsonde boundary layer height. So we saw that for 3 different towers and days, there was a distinct difference between the model footprints, or between the Corman and Wiesner model and the Kiljoen model. As the Corman and Wiesner model, which the footprint from that model is outlined in red on this on the footprints here, that overestimated the source area. And so we see that in this example, the contributions or the influence from the coniferous forest are not actually significant when you take into account the Kiljoen et al. Model that is considering the boundary layers, boundary layer heights. But there is no well, I guess, yeah, then looking at the second footprint, similarly, there's not as large of a contribution from the coniferous forest for the Kiljoen model. And then there's also less of an influence or not a significant influence from the lake. However, changing the boundary layer height from 1,500 meters to the windsonde measured boundary layer height, it didn't actually significantly change the footprint size using the Kiljoen model. And so we validated this with all the towers for all of the days and saw similar results.
Yeah. So this is pretty cool stuff. And then we're thinking we have all these data points. So this is one of the days you're looking at here, the potential gradient versus altitude. And the windsondes we use are relatively small. We attach them to small balloons, so they don't rise as fast as other more expensive ones. So they actually cover a larger area. So if we look at all the different vegetation types, these windsondes overflew in this case, were about 5 different ones. So we were like, well, maybe we can learn something from these different vegetation types and the temperature and humidity measurements. So this, again, is the potential temperature gradient. And then now we can just look at the temperature gradients of the same day, as well as the relative humidity gradient. And we want to note here, this is all a little exploratory here. We were just curious if we can do that. Basically, our hypothesis was, can we determine temperature and relative humidity gradients by vegetation types using windsonde data? One thing I need to point out is, of course, this data is highly correlated in time and space. So to do this, we actually used models that accounted for that high autocorrelation as well. And it seems like we got some results that make sense. So you can see in this example, we calculated the temperature gradient. I have to note that this was below the boundary layer height, because we assumed that the vegetation types will be, or the windsondes, the temperature measurements and humidity measurements will be more dependent on these vegetation types. And you see that for temperature gradients, if we look at the open water, it makes sense that the temperature on the surface would be lower compared to urban areas or agricultural areas. And you can see that there's also a change or a difference in these different gradients as well. And similarly, we can do this for relative humidity. Again, just showing you for open water, for example, relative humidity at the ground level was larger compared to urban areas or agricultural areas. And when we say urban, those aren't big cities where we work, those were more villages. So now we have these temperature and relative humidity gradients. We could potentially calculate a Bowen ratio from that based on the different altitudes, and we also calculated the vapor pressure. So again, this is very exploratory because unfortunately we didn't have too many data points, but so we determined the temperature and humidity gradients by the vegetation types below the boundary layer height, and then we compared these to the eddy covariance measurements, the Bowen ratio measurements of the eddy covariance towers that the wind zones passed. And again, I want to point out we accounted for the correlation and temporal and spatial autocorrelation. And here's a graph of what we found. Again, we only had about 5 different points to compare to because unfortunately some of the towers didn't have measurements for some of the wind sound launches. But you can see that there seems to be a correlation between the different vegetation types, the Bowen ratios, as well as how they correlate with the eddy covariance towers. So in these gray dots are what the eddy covariance tower at that particular location recorded. And we can also see that it correlated well with the temperature. So we're seeing a higher Bowen ratio for July 12th and then lower Bowen ratios for July 11th or 13th. So to summarize, the Corman-Meixner footprint model, we found overestimates the source area contribution. It seems to be that assuming a boundary layer height of 1,500 meters for footprint calculations seems to be a safe bet because there was no significant difference between the footprints. And then what we saw was that we could potentially use wind sound temperature and relative humidity measurements to calculate the Bowen ratio, evapotranspiration by vegetation type. But because we have very few data points, this is a call for collaboration. If you have wind sound data, please contact us. It would be great to maybe look at this a little bit more in detail. And then, if anything, I think wind sounds will definitely help you understand your footprint better because we got to amazing locations in the experiment just because you have to retrieve these wind sounds. So this was one of the wetlands we discovered by trying to recover one of the wind sounds. And with that, that was our contribution. Thank you so much.
No, thank you.
Thank you. Yeah, I don't know how many people are using wind sounds. I bought some and I will use them this summer. So I'm happy to.
Yeah.
I think it's a great idea to collect all the data that's out there and like combine it and see what new things we can do. So
yeah.
So the questions will come in the end after the talk. So if you have any questions for this talk, just post them in the chat or post them on the poll everywhere. And now the next talk will be by Adam Young, who is a postdoc at Northern Arizona University, working with Andrew Richardson there. And yeah, I am Kung. Perhaps you can play the recording.
Okay, do you all see the screen right now?
Similar issue as earlier, that there is like a bar on the right side that is kind of gray, but not still.
How about now?
Still kind of patches on it.
Okay.
Wonder if it will disappear. No, it's good.
Okay.
Considered how phenology acts as a. Hi everyone, I'm Adam. Today I'm going to be sharing with you some of the work I did as part of my postdoc at Northern Arizona University in the Phenocam group. My research in the Phenocam group primarily looked at and considered how phenology acts as a control of water and heat fluxes in different ecosystems across North America. Before I begin my talk, I do want to just give a brief overview of what Phenocam is and what it can tell us. Phenocams are digital cameras that are set up to overlook ecosystem canopies. Currently, there is a large network of cameras mostly located in North America. Each of these cameras are designed to take pictures and images approximately every 30 minutes. These images are then stored and later quantified to get estimates of greenness from the canopy. Specifically, we can look at each image and then identify a region of interest, which is highlighted by a yellow box here as an example at Harvard Forest. We then quantify what's called the green chromatic coordinate, and this can just be thought of as a relative greenness metric. On the right, from Harvard Forest as well, we can see how greenness changes over the course of a single year. We see it does capture distinct patterns in the dormant season, those phenological transitions, the growing season, and then back into dormancy after senescence. Furthermore, we can further process these data, smooth them out, and identify distinct phenological transition dates, such as spring greenup and senescence. So we're going to be seeing a lot more Phenocam in this talk, and I just wanted to get you set up exactly so we all understand exactly what it's showing and what it can provide. As a postdoc in the Phenocam group, I looked at a lot of images of different ecosystem canopies. And it was always pretty amazing and incredible and kind of fun to look and see how dramatic these changes are over time and across many different ecosystems. Just looking at these images, we can see that the full structure of the canopy really changes during leaf out, that green-up transition into the growing season. And while we can physically see there are these really big structural changes in the canopy, we also know there are important changes as well. For example, after phenological transition, there's likely going to be a change in albedo, which will influence or change the surface temperature. The change in the physical structure of the canopy is going to influence surface roughness, which will ultimately influence aerodynamic resistance. Also, there's a large shift or change in the biological function of the canopy and how water is transferred from the soil to the atmosphere. As part of my postdoc project, I first looked at how phenology influences surface roughness and sensible heat fluxes. Specifically, could we see whether seasonal changes in surface roughness track phenological transitions across a wide range of ecosystems? To do this, we used Ameriflex data and calculated what's called the KB inverse parameter. This is just the ratio of two different roughness heights, specifically the roughness length for momentum and the roughness length of heat exchange. Quantifying KB inverse at a roughly 3-day timescale, we can see how it changes seasonally at two different deciduous broadleaf forest sites on the bottom here. We can also see how it seems to be inversely related to canopy greenness in these ecosystems. We can further identify and pinpoint that these seasonal shifts, at least during the springtime, in KB inverse are likely being driven at least partially by phenological transitions. For example, we can see in the year 2012 that the day of year transition was 74. These numbers are listed at the top of each vertical line. These are the transition days identified by Phenocam I highlighted previously. And we can see that this is significantly earlier than other years that I'm showing here. However, even though it's much earlier, we see that transition does occur around that same date. This is indicating that these shifts in surface roughness are likely tracking phenological transitions in some ecosystems. We also know phenology has a strong influence or effect on latent heat fluxes or water fluxes. Again, these are two examples from deciduous broadleaf forests. We see that during greenup and as we move into the growing season, there's a large increase in evapotranspiration and a strong decrease in sensible heat flux. Looking at these patterns, I began trying to better understand what is the full seasonal trajectory of changes in latent heat flux or in the surface energy balance over the course of the year, and can we directly predict this or track this using canopy greenness estimates or better understand the role of phenology? Here I have some plots that are highlighting phenocam images that are taking before and after green up for 4 different ecosystems that are not deciduous broadleaf forests. In here we're looking at evaporative fraction, which is just the proportion of available energy that's partitioned as latent heat flux. We can see that in some ecosystems, such as the grasslands, there's a really strong correlation between greenness and evaporative fraction. However, we can then also look and see some ecosystems where this pattern is not as clear, such as a coniferous forest site that is depicted at the top. So my question became, is phenology essentially an important factor to consider when predicting seasonal patterns or trajectories in water use or water flux across a wide range of ecosystems? And if not, what variables are most important and where should we consider and where are they most important? Which brings us to our main research question. How do the relative controls of evapotranspiration and seasonality vary among different plant functional types as well as across a broad aridity gradient? Our study covered most of North America, or covered a large part of North America, and we had a wide range of sites and PFTs ranging from the northeast all the way down to the southwest. In total, there were 20 different sites for 114 site years. And this aridity gradient that I'm depicting here is the long-term average potential evapotranspiration, or PET, divided by the long-term average precipitation. Specifically, this tells us whether PET is greater than or less than the water actually being received via precipitation in different ecosystems. A good way to think about this or classify this is that in ecosystems where PET is less than P, these are more likely, not necessarily, but more likely to be energy limited ecosystems or have an energy limited hydroclimate regime. While in areas where PET exceeds precipitation, it'll be the opposite and it'll be a water limited hydroclimate regime. Go into some of the results, I do want to highlight 2 quick details on the methods used. First, we didn't explicitly model or look at evapotranspiration. We considered 2 other measures, evaporative fraction, which I shared with you previously, and bulk surface conductance. We chose to use EAF because it is normalized by available energy, which might have a strong influence on some of our results at the seasonal timescale. And it also provides a good measure of what's happening with the land surface energy balance over the course of the year. We then used surface conductance because we felt this was a closer mechanistic variable to how changes in phenology, how changes in leaf out and leaf area index over the course of the year may influence ultimate conductance of water-based vapor to the atmosphere. And we got surface conductance by using the Penman-Monteith model. The second methodological point I want to highlight is that we use path analysis. So this is a bit more complicated than maybe a standard regression model, but it is not a process model, it is strictly empirical. Effectively, what path analysis does is it links together multiple different linear regressions. We chose to use path analysis because we felt this might more better or accurately capture the natural complexity of the system we are considering. It also allows us to use a method called mediation, and this is to estimate the indirect effect of a given explanatory variable. For example, we can look at GCC, which is that canopy greenness value. We can see the direct arrow to bulk surface conductance, and then we can also see that GCC is acting through VPD as well. So there's an indirect effect of greenness on surface conductance in this model that's mediated by vapor pressure deficit. We can then calculate the indirect effect and direct effect to get a total effect and better understand what the most important causal relationships are in different ecosystems or different hydroclimate regimes. And just a quick note, we also did include some other variables. I probably won't discuss many of these in too much detail for my talk, but the important one to understand and to memorize is that P10 is cumulative 10-day precipitation. And we'll be looking at a lot of results or considering how precipitation influences GS in different ecosystems. Now, these models are pretty complex, so we don't have time to look at all of them. So what we're going to do is we're going to first focus in on 2 sites that generally span the aridity gradient of our study area, specifically an arid shrubland site in southern Arizona and a deciduous forest site in the Midwest. First, let's see what's going on with our path analysis at the deciduous forest site. I know there's a lot going on in this figure, but there are two key pieces here that I want you to look at and focus on. First, the colors of these arrows indicate either a negative or positive relationship. Red indicates a positive relationship, while blue indicates a negative one. Second, the width of those arrows indicates the overall value or magnitude of the coefficient directly linking a given explanatory variable to a response. So the more influence or effect a variable has on a response variable, the thicker or wider that arrow will be. Right off the bat, we see that some of these temperature variables like GDD and CDD have a really strong effect or impact on canopy greenness, or they act as strong predictors of canopy greenness in this deciduous forest ecosystem. Subsequently, we also see that canopy greenness acts as a really strong predictor of bulk surface conductance, which ultimately affects evaporative fraction. We can also see that our precipitation variable, P10 at the top there, has very little influence throughout this network. So what I want to look at next is now we're going to transition to our shrubland site and see how that differs from what we found at this deciduous forest site. We can now shift to looking at what's going on in some dryland or arid ecosystems in the southwest. So here we have a shrubland site, and right off the bat we see that the influence of temperature variables such as GDD and CDD have a much lower influence or lower effect on greenness in these ecosystems. The second big change that we likely noticed, or that you likely noticed, is that the influence of precipitation now has a much greater effect. Those coefficient values are much higher than they were in the deciduous broadleaf forest ecosystem. However, we also still see that the effect of bulk surface conductance on evaporative fraction remains really high, similar to what we just saw in the deciduous forest. So the key takeaway here is that when we move to the southwest, greenness does seem to have some influence on bulk surface conductance and ultimately evaporative fraction, but precipitation or water availability is playing a much stronger or more important role in these ecosystems. For the final part of my talk, I want to just summarize this total effect value, which is the direct and indirect effect that we get from mediation in the path analysis, and look at how this varies across that broad aridity gradient of our study area. So on the x-axis in these figures, we have the site level aridity index, PET divided by P. And then on the y-axis, we have the total effect of two different variables on bulk surface conductance. That's precipitation on the left and canopy greenness on the right. We see that the overall influence of precipitation and canopy greenness differs depending on site level aridity. In water-limited ecosystems at our driest sites, precipitation emerges or is identified as the most important control of bulk surface conductance relative to the variables that we were considering. When we look at canopy greenness, we see that is much more important or prominent in these energy-limited systems. And this is one of the key takeaways from this study. We found this continental scale pattern in the role and influence of phenology and other variables in terms of how it controls and affects bulk surface conductance and ultimately evaporative fraction in these ecosystems. With that, I'm going to summarize what I've shared with you today. So through data exploration, we found that there are these really strong seasonal patterns in evaporative fraction and phenology in many ecosystems, although they don't always line up and track each other. In many ecosystems, we found that phenology does emerge as a really strong predictor of bulk surface conductance. However, this importance of phenology does vary considerably, and this is as a function of site level aridity. Thank you for your time, and I hope to answer any questions you might have.
Thanks, Adam. Again, if you have any questions, use the chat or the poll everywhere. I see there's some of the questions are already being answered on the poll everywhere. So if you want to read up on that, it's all there. And if you want to add new questions, please feel free to add them. So the next talk will get us a little bit more away from the surface, I would say. So Ryann Wakefield is a postdoc at NOAA, and she will talk about mixing diagrams and how we can use them, combine them with observations also. Thanks, and the floor is yours.
All right, thank you for the introduction. Today I'm going to be talking about this kind of revised application of the mixing diagram methodology and how it can be used to kind of maybe get a better approximation of entrainment fluxes, but also its applicability to Ameriflex in general. So, oops. So first of all, just want to, of course, acknowledge my co-authors as well as the financial support for allowing me to do this work. So mixing diagrams are not really anything new. It's not anything that I've created, but it's a really great framework that was introduced in 1992 by Alan Betts and then further elaborated on by Santinello et al. In 2009, 2011, but also several other papers on top of that. And they're basically used to quantify the different contributions to the PBL moisture and energy budgets. So, trying to differentiate between the surface flux contributions versus the entrainment contributions, and looking at how all of those influence the temporal evolution of temperature and moisture in the daytime boundary layer. And they're really useful because they can be used to compare observational and model representation of these processes, but they're also just useful for simple scientific curiosity if we're trying to understand exactly what's driving changes in temperature and moisture in the boundary layer. So a lot of times we see these used with model output, and this is largely because we have a lot of limitations observationally. The first limitation being that we need surface flux observations, and we also need boundary layer height estimates. So, we tend to have a lot more observations of 2 meter temperature and specific humidity than we actually have of surface fluxes. And so this is where Ameriflex is especially useful. But we also have to have boundary layer height estimates, and that usually requires us to have profiles of temperature in the boundary layer. So this can also be a challenge because we don't typically have a lot of radiosonde data at high temporal and spatial resolution. So the traditional framework really just relies on 2 meter temperature and 2 meter specific humidity measurements. And this is used to kind of estimate boundary layer characteristics. So we're assuming that the boundary layer is well mixed, and therefore we're assuming that temperature and moisture close to the surface is going to be representative of the entire mixed layer. And we know that that's maybe not necessarily true since our 2 meter observations are in the surface layer. So they're going to be kind of amplified in terms of the diurnal cycle. They might be a little bit cooler in the morning and a little bit warmer in the afternoon than the actual entire mixed layer. So we began to look at this from a different perspective and suggested kind of a different approach that uses mixed layer mean temperature and moisture, which of course is going to require vertical profiles. And we wanted to test this approach, and we showed in a paper that's almost ready for submission, we showed that LES application of this new mixed layer mixing diagram framework actually does better approximation of budget closure for moisture and energy budgets. And that's really good news because this means we can better estimate entrainment fluxes through this new kind of revision to the framework. Oops. So before I go too much further into talking about mixing diagrams, I should probably actually elaborate on what they are. So what you're looking at here is this, this plot that basically shows the co-evolution of temperature and moisture in the daytime boundary layers. So here we have this black curve, and T naught is typically sometime in the morning, TF is typically sometime in the afternoon. So we follow along that black curve, and that shows us this kind of temperature and moisture evolution within the boundary layer during this time. So on this particular day, we can see that early on, we started to see a little bit of moistening of the PBL as we kind of went in the positive X direction. And then we saw mostly drying for the rest of the day. And then if we go in the positive Y direction, that shows us that the PBL was warming. And so by looking at just kind of the direction of this black curve, we can kind of estimate basically the coevolution of temperature and moisture in the boundary layer. Typically, like I said, we use 2-meter temperature and moisture values, but in this particular plot, I'm kind of giving you a teaser or a peek at what it looks like when we used mixed layer mean values. So you can see here that there's somewhat of a difference between 2-meter and mixed layer values. 2-meter is shown in gray and mixed layer is shown in black. So you can see that overall the 2-meter temperature showed just a little bit more warming than the mixed layer temperature. And then it also showed a little bit less drying. And so that would kind of impact a lot of other quantities that we're going to be estimating from these mixing diagrams. And I'll get into that further. So here we have this total vector, and this represents this kind of total change from beginning to end of the day. Now, we typically don't show this in the mixing diagram frameworks, but I'm providing it here so that we can kind of get a better estimate of how we're kind of deriving all these other quantities. So this is just kind of showing this total change throughout the day. So our vector is pointing towards the upper left portion of the plot, which means that overall our boundary layer warmed and dried. And then we have the surface flux vector, and this is actually using observed surface fluxes in this case, and we're scaling them to the depth of the boundary layer. So we want to know how temperature or how heating basically got distributed through the boundary layer, or how evapotranspiration caused moisture to get distributed within the boundary layer. So here our Y component is equal to sensable heat fluxes, and they're scaled to the depth of the boundary layer here in order to put everything into energy quantities. So you'll see here everything's represented in kilojoules per kilogram so that we can kind of compare surface fluxes to total daytime temperature evolution. Everything is in the same units. And then X component is equal to our latent heat fluxes scaled to the depth of the boundary layer. And then finally in this plot, I've included radiative heating and advection. We do have the ability to estimate these quantities at certain locations. So here this study was focused on the ARM Southern Great Plains site, where we actually were able to kind of derive advection and derive radiative heating, but it's not always necessary to include these, especially if you're looking at a calm day. And then finally, this is where kind of this purple vector comes into play, because when we add up the total vector with the advection vector and the radiative heating vector and the surface flux vector, we're kind of trying to take basically the difference between the total vector from, or sorry, I'm trying to explain this well. Basically, the residual vector is just kind of looking at, the contributions of surface fluxes, advection, and radiative heating towards the total evolution of the boundary layer. So we're kind of subtracting those from this total vector in order to get this kind of residual quantity. So for example, most of our heating on this particular day was driven by surface fluxes. And then there was a little bit of warming due to advection and radiative heating. And then whatever was left was actually obtained as the residual vector. So entrainment was kind of this last warming. And so here, X component is entrainment contributions to the moisture budget, and Y component is entrainment contributions to the energy or temperature budget. So again, we're kind of doing this proof of concept study here, and we're focusing on the ARM Southern Great Plains just because we had the data to do so. In particular, we had the atmospheric emitted radiant interferometer, which is this ground-based remote sensor. And the nice thing about this is that we could get vertical profiles of temperature and moisture at a really high temporal resolution. We typically don't have that from regular radiosondes. We usually only have 2 a day. So this was nice because we could obtain vertical profiles at a 5-minute resolution if we desired. And then we also had our surface flux observations, and we're able to derive advection and radiative heating, but I won't go too far into the details of that. But basically, the nice thing about the ARI is that we wanted to get this kind of mixed layer mean quantity, and ARI allows us to do that by having high temporal resolution of vertical profiles. So instead of relying on our twice-a-day radiosondes or relying on a field campaign, we can actually get temperature and moisture profiles at every 5 minutes if we chose. And this also lets us estimate boundary layer height, and this is going to help us maybe better approximate PBL budget closure, because we're not just using information from close to the surface. We're looking further into the boundary layer to actually get this kind of mean temperature and moisture value. So we had to define our mixed layer. And at first we thought, okay, let's look at the entire depth of the boundary layer from, 0 to the entire PBL, or what we would call ZI. So I'm going to refer to ZI. That's just the boundary layer height. So we at first tried to look at 0 to 1 ZI for just being the mixed layer, but lots of studies have shown that bias and water vapor mixing ratio and potential temperature tend to increase drastically above 0.5 ZI, or about halfway through the boundary layer when we're using the ARI. And so we had to kind of redefine what we were going to choose for our mixed layer here. And this is largely because we don't want to introduce information that's maybe being brought in from above the boundary layer, which is what's happening because we have a reduction in vertical resolution as we go above 0.5 ZI for the ARI. So we chose to define our mixed layer, the layer in which we're going to take the mean temperature and mean moisture as being below 0.5 ZI. And this seems counterintuitive if we're trying to, add more information, but we're really not looking throughout the entire PBL. But it's still a better approximation than just simply looking at 2-meter observations. And so this is also kind of giving us a good representation of what the actual mixed layer mean temperature and moisture looked like. And the way we verified this was actually comparing our results to radiosondes as well as ARI profiles that were augmented with Raman LiDAR profiles. So we had higher vertical resolution and moisture from the Raman LiDAR, and that's what I'm showing on the right. You can basically see that below 0.5 ZI, the ARI and the ARI plus Raman LiDAR compare really well. And so that we can be confident that our 0 to 0.5 ZI mixed layer definition was actually representative. And then here, you can see that, again, we still showed similar temperature and moisture evolution with radiosondes, as well as similar boundary layer heights. So we only had 3 times sampled on this particular day in the period of interest, but we see relatively good agreement with maybe a slight moist bias in the ARI. And again, the Raman LiDAR retrievals were very similar to the ARI retrievals, so we know that we were at least getting a representative profile of temperature and moisture, so we could be confident in our mixed layer mean estimates here. But again, observations are not perfect. We have plenty of sources of uncertainty. We have instrument error, vertical resolution errors, as I've mentioned, calibration uncertainties, sampling error, because again, depending on wind direction, we might be sampling a different land cover type, especially at the SGP site in Oklahoma. So we have all of these different sources of uncertainty, and how can we represent those when we're using this mixing diagram approach? Because ultimately we're trying to estimate entrainment, but we know that we're probably not going to get a perfect estimate. So how can we quantify exactly kind of how much uncertainty we have in our entrainment estimates and whether or not that amount of uncertainty is acceptable? So here, again, just a reminder, our black curve is that mean mixed layer evolution. And for estimating uncertainty and entrainment, it was kind of a multi-step approach. So within the ARI, we have information from these retrievals of temperature and moisture about uncertainty at each level. And so we were able to use that to estimate kind of this initial uncertainty in our initial temperature and moisture. Because as you can see here, our surface flux vector is added to that initial temperature and moisture. So this is kind of the daytime total surface fluxes scaled over the boundary layer, translated into energy units. So we knew that we were going to start with some uncertainty in terms of that initial temperature and moisture value. We also know that our surface fluxes are going to have uncertainties themselves. And so you can see this kind of colorful cloud at the tip of the surface flux vector. That's meant to represent kind of the amount of uncertainty that was accumulated as we looked at our surface flux observations throughout the day, and then added those to this kind of initial temperature and moisture. So this is kind of this cumulative uncertainty that we're seeing here. And so actually, with respect to the length of the surface flux vector, our uncertainties are pretty small. Blue being less than 1 standard deviation here. So those uncertainty values are on the order of probably half an energy unit when we're looking at a surface flux vector that has a length of approximately 5 or 6 energy units. And so here, we also had uncertainties due to advection, and ultimately all of this was accumulated into our uncertainty for our entrainment estimates. And then here I omitted radiative heating uncertainties because the magnitudes were so small that it was going to be negligible. But overall, really the whole takeaway message here is that we're able to get a little bit better estimate of closure of moisture and energy budgets using this mixed layer approach. As you can kind of see in this example, the diurnal cycle and temperature was a little bit more amplified for 2-meter values. And so we kind of took care of that by looking at the mixed layer mean values only. And then we basically also showed how we can incorporate information about uncertainty, because we're trying to estimate entrainment. We want to make sure that we're actually doing this properly and that we're actually accounting for the fact that even though our obs are often used as truth for comparison to model output, they're not perfect. And so how much uncertainty is acceptable, how much difference between the model and the observations is acceptable, those questions can kind of be addressed by incorporating uncertainty into this analysis. And then finally, one thing that was brought up in past discussions, I think with Manuel, was that basically tall towers might be useful as well for sampling kind of above the surface layer. So we can kind of get an estimate of the mixed layer here in order to kind of, have this pseudo mixed layer mixing diagram. So this might also be another great way that we can use Ameriflex observations. And with that, I can take questions.
Thanks, Ryan. So yeah, as always, post your comments or questions either in the chat or in the poll everywhere. I think we already have a good selection of questions there. And last talk will be by Yunyan Zhang, and she is a staff scientist at Lawrence Livermore National Lab, and she will talk a little bit more about modeling studies and also linking it to the land surface. The floor is yours, Yunyan.
Hello, can you hear me?
Yes.
Great. Thank you very much for the invitation today. I'm going to talk about local convections and their interaction with land surface. Many thanks to my collaborators and co-authors, especially my postdocs, and also thanks to my funding source from DOE Early Career Research Program, and also the ARM and ASR research program. Why we are interested in local convection regimes, they are very important for the summertime climate over land, and more importantly, from the modeling perspective, can you see my mouse? Okay, yeah, yes. So usually the large scale model, the global climate model, have very poor performance in simulating diurnal cycle of clouds and convection. The major problem is that the precipitation triggering is around noontime, which is in phase with the surface flux variations during the day. So, and this behavior is biases, it's few hours earlier than the observed late afternoon deep convection onset. So we usually attribute such model deficiency to the lack of representation of the gradual development from shallow cumulus and transits to isolated deep convection. So even with the emerging game-changing global cloud resolving model nowadays, at kilometer resolution, the shallow cumulus clouds, because of their small size and also their short time of life, still remain subgrid scale processes and has to be parameterized. And also today, we are going to focus on these active and forced shallow cumulus, and they are usually coupled tightly with the boundary layer development and land surface forcing. And usually they are not precipitating. So conceptually, they are very ideal and simple to be a test bed for many of the cloud parameterizations, such as turbulence and shallow convection. And so from the observational perspective, in the following, we are going to focus on the ARM suprasite at Southern Great Plain, which is the red star here. We usually call it SGP, with comprehensive co-located observations, both at surface, such as E-core, E-BIR, and also with the boundary layer profiling such as Doppler LiDAR, Raman LiDAR, and also the ARRI that Ryann just mentioned. And we also have the vertical pointing cloud radar, and together with the stereo cameras to catch up the 3D morphology of clouds development, especially for these shallow cumulus clouds. And here we want to carefully distinguish the local regime versus non-local regime. The non-local regime here, especially at SGP, referring to those mesoscale convective system that might propagate into the SGP without strong connection with the local surface processes. And so we want to focus on these locally generated convection regimes, and also want to improve on our understanding on these fast interactive process and physics, and also within one diurnal cycle. And also we want to understand better its further feedbacks on the longer time scale and larger spatial scales. So in the following, I'm going to talk about the controlling factors of these convection regimes. And first, there's always two perspectives. One is atmospheric control. I'm going to briefly summarize here based on a series of papers that we have been doing with the long-term data at SGP site, and also the 2-year measurement at Go Amazon site, which is a rainforest region in tropics. And so we find that the free troposphere and boundary layer relative humidity is still the dominant factor, not only controlling the transition from shallow to deep, but also controlling the onset time of the precipitation and how many pulses in the afternoon precipitation. And you can see the figure on your left. It's well illustrate such mechanism that the transition from shallow to late onset afternoon deep convection to early onset with the double pulses and to early onset with the single pulses. And you can see the relative humidity is increasing. This is based on the observational study we just published on GRL on the Go Amazon and together with SGP analysis. And so in the following, I'm going to focus on the perspective of land surface control. And in the past few years, especially focusing on SGP site, we have developed analysis on moisture budget variability, the detailed mechanism of the interaction, and also the validation of convection theories, and also use them to constrain climate model parameterizations. Today, I'm going to focus on 4 studies, especially on this local process chain proposed by Santinello et al. A few years ago, that if there's basically 2 routes of this local process chain from the land surface to the precipitation and clouds. One is this anomaly apart from the mean state, that if you see the change in soil moisture, then it will cause a change in the partition of evaporative fraction between sensible and latent heat fluxes, and further cause in the PBL entrainment and development change, and thus the thermodynamic change to impact on clouds and precipitation. And there is another second route, which is involving the surface spatial heterogeneity in either soil moisture or in the land cover change. So the differential heating between these neighboring patches not only induce the changes in the thermodynamic field, but also induce a secondary mesoscale circulation that could naturally converge over these warm and dry patches, compared with the neighboring patches, and then lead to the formation and change in clouds and precipitation. So today, I'm in the following four studies, I'm going to first go through the first route and then the second route. So on the anomalies of the surface conditions, this study is an observational study that we use 10 years observations around ARM SGP site to study especially the coupling within the analysis framework of local convection regimes, including clear sky, fair weather shallow cumulus, and late afternoon deep convection. Especially for the large SGP region, we further divided them into 5 subregions here, especially taking into account soil moisture gradient, which is the color contour shows here, and also the land cover type. For example, I want you to focus on subdomain A and B. A is dominated by grassland, while B is a mixture of forest and grassland. And when we compare the shallow cumulus observation in the summer, we find significantly larger cloud fractions over the B region, which is a mixture of forest and grassland. And also on the deep convection analysis, by establishing the strong correlation across the chain effect from surface to precipitation, we find strong correlations from evaporative fraction to surface and PBL RH, and then leads to early onset, especially over the region A dominated by grassland. And then we further ask, with these observed statistics, can we further evaluate the performance of climate models? In this study that we specifically applied the local metrics, and thanks to Ryann, and she explains in detail what is the mixing diagram included in the local metrics. And we use these metrics together with ARM data to assess the performance of CAM5 and E3SM version 1 regional refined model. And CAM5 is run in weather forecast or hindcast mode, and the RMV1 model is run subject to nudging to the outer domain, and the inner domain is 1/8 degree, which is about 10 kilometers. And so the specific setup is to of these models is to host a day-to-day comparisons with the ARM real observations, and also within this local convection analysis framework. Especially on clear days, we use mixing line diagram. We find that CAM5 significantly overestimate the boundary layer top entrainment drying, while the E3SM V1 underestimate the surface evaporation. While on the shallow cumulus days, we use the local diagnostic called LCL deficit, PBL LCL deficit. We find that in the models that the shallow cumulus are usually formed with much weaker PBL growth and more humid morning conditions while compared to SGP observation. And for the late afternoon deep convection regime or days that we apply the local diagnostics called CPT-HI framework, and we find that usually inside the E3SM V1 model, the convection is usually triggered by the elevated instability rather than the lower troposphere stability that tightly coupled with the land surface. And so these two studies are focused on the anomalies apart from the mean state. The following ones is actually focusing on the effect of land surface heterogeneities. And we are asking the question is, what is the role of the heterogeneity land scale and background wind playing such effect? And this slide shows you a large ID simulation modeling study with the chessboard-like alternating wet and dry patches setup. And this shallow cumulus cases is based on a long-term composite observational case. And also the wet and dry surface fluxes setup is according to the observed surface sensible latent heat difference based on SGP observations over winter wheat and grassland. So you can see the cool animation here in the upper row. If we fix the background wind to be quiet, and then we increase the patch size from right to left, you can see as the patch size increasing, the cloud top height, which is the color contour shows here, is increasing. And furthermore, the convective systems is growing to a larger size. And if we fix the background, if we fix the patch size by increasing the background wind, you can see the deeper convection is actually moving to the edge of the patches, and got totally surprised when such background wind is exceeding a critical limit, such as the secondary circulation strength for a given heterogeneity length scale and amplitude of the difference in surface fluxes. So this is a modeling study, and the next question we'll ask is, do we observe such impact from observations? Okay, so this study, actually, we use high temporal spatial resolution data, such as the GO16 reflectance, and also arm surface observations, and also the high-res land cover data from USDA CDL datasets. Usually GO16, the operational product, does not provide shallow cumulus retrieval, and we had to develop a retrieval algorithm based on the reflectance and cross-cord validated through the arm surface observations, so we can derive these shallow cumulus cloud fractions in the region, around the SGP region. I want to remind you that the analysis domain is exactly the B domain I just mentioned a few slides ago, with a land cover mixture dominated by forest and grassland. And you can see that these three figures in the upper row shows a diurnal change of the shallow cumulus cloud fraction. Green is for forest and red is for grassland. For all the cases, without any filtering, you already see some difference. But if we further restrict it to the analysis to larger patches of the land cover, or with the lower wind speed, you can see the difference become even more pronounced. And we also further asked the question, is the land heterogeneity land scale playing any role in such an analysis? And in this figure, the lower right one, you can see we partition these differences between the two into different land cover land scale bins from 2 kilometer to 30 kilometer, which is also the patch size of these land covers. And you can see that the solid line here represents a time focused on noon, which is between 11 and 13 local time. And the dashed line here focuses on time period of early afternoon, which is between 13 and 15 local time. Around noon time, the difference between forest and grassland is mostly concentrated on the land scale less than 9 kilometers. Well, for the early afternoon difference, such preference become much larger when the land scale is greater than 9 kilometers. If without the secondary circulation, we would see the difference between green and red line between forest and grassland will be the same across all the land cover heterogeneity land scales. But the change, the shift from a smaller scale to larger scale, from noon to early afternoon, we think it's attributed to the max time in the differential heating between the patches around noon, but it takes longer time for the secondary circulation to propagate and converge over larger patches. That's why we see a temporal shift and a little bit lag in this difference at the larger scales. And such observations of clouds is further confirmed by the arm surface observations, especially we have equal Ebra sites over forest and grassland in the analysis domain. And you can see, especially the left corner figure shows you the sensible and latent heat contrast. Over the forest land cover, we see both stronger sensible heat, which is in the solid line, and the stronger latent heat, especially before early afternoon. And you may ask, what about other land covers in the analysis domain? Especially we have a city, Tulsa, Oklahoma, about 20 kilometer size. in the middle of our analysis domain and also some open waters. And you can see the diurnal cycle of the cloud fraction that over the city in the afternoon, the shallow cumulus cloud fraction is really become more pronouncedly different and higher. And the animation shows you that the center is the city. And if we're moving away from the city center into the rural areas, you can see the cloud fraction actually dropped a few percent from the center to the rural areas. And so to summarize, the take-home message is that the local convection regime classifications is very helpful, and it facilitates the detailed examination of faster interactive physics, especially at the supersize using co-located observations. And on the model diagnosis, we think the hindcast framework is very valuable, especially if we want to match this day-to-day comparison with real data. On the other hand, we also provide observational evidence on the impact of land cover heterogeneity land scale on the shallow cumulus occurrence and development. In the future, and some of our ongoing work is focusing on extended analysis, especially the observational one, to the deep convection triggering and precipitation. And we will also extend our model diagnosis to global cloud resolving model, which is kilometer scale. And thank you so much for the opportunity.
Thanks, Yunyan. So now we still have like a good 15 minutes for discussions. So there was quite some activity, and perhaps I would go through the questions more in the order of the talks, but obviously for all the presenters, feel free to chime in if you have an opinion about that. Some questions were already answered in the chat or in the poll actually. There is one for Susie and Juliet. It's, can you elaborate on the implications of your Bourne ratio results for understanding how landscape heterogeneity can influence the boundary layer? It might be a little bit related also to how variable the boundary layer was across the study area. Did you see any trends? Was it fairly homogeneous?
Yeah, Juliet and I were discussing this one because we both don't really, this is not our main topic that we look at. So, but I think Yunyan's talk was really interesting because it kind of goes with the question. But from the 5 days that we looked at, I mean, obviously the boundary layer height differed by time of day, but over the course of the days, it ranged from what was like 900 above ground level to like 1100. And I think that was like pretty consistent throughout at least the week that we looked at. And yeah, that question is interesting. I mean, we were talking, I think it really depends on the patchiness of the vegetation and the soil moisture conditions and whatnot. So
if of course, if the majority of the land perhaps were barren or dry, then you'd expect like a higher boundary layer height, potentially just because it might be just naturally more convective near the surface than if the area was dominated by lake. But perhaps if there's agriculture plus lake, then the boundary layer might be a little bit lower. This is all just, you know, kind of like initial thoughts on that. But in any case, the heterogeneity of the land,
we would expect it to contribute to it, but the question is, how?
I guess it's also difficult with the wind zones because they're traveling. So
exactly.
If you take a GPS and pinpoint the boundary layer to what's exactly underneath, is probably not the reality, because it's probably probably tracks more the balloon, like where the influence comes from. So, I guess there's lots to explore. So I'm
Mhm.
looking forward to have more sites with balloon soundings and see
Yeah,
more coming out.
it's a lot of fun.
Yeah, and I think a few questions you already answered, like the footprint model is not very sensitive to the boundary layer. I guess that was responded here too.
Yeah, that's what we found.
Yeah, I think you did a good job answering to most of the questions.
We tried.
And then I don't know, Adam, are you around? There are a few questions for your talk.
Yeah, I'm here.
Okay. Yeah. So I think one question here is, was there an aridity gradient in the strength of the precipitation control on the greenness index too?
Yeah, that's an interesting question. And I feel like I looked this up a long time ago, some iteration in this analysis. And so to give a better answer, I did just pull it back up and plotted it up. And there's a really strong relationship between total effective precip on greenness, where it has a much stronger controller effect in dryland or more arid ecosystems. I think the R squared I pulled up was like 0.64. So it's a pretty tight relationship.
So it seems like there is a strong control on greenness index, but greenness index in the dry area, in the dry ecosystem doesn't have as strong as a result on surface conductance. Was that it?
Yeah, the overall strength or total effect when you add up the direct and indirect effects of precip in these dryland ecosystems, it's much higher than it is in wetter ecosystems like in the Northeast. That's kind of the main conclusion there. And that's, you do find some relationship with greenness having a controller effect on conductance, but it's not as great as precipitation in a lot of cases in these ecosystems.
Another question here, more about the study design. Could you describe how the Ameriflex sites were chosen for your work? For example, no sites from the southeast of the US. Would you expect findings to hold in other regions too?
Yeah, it's a good question. We did try to dig through as many of the Ameriflex sites that had publicly available data as we could. And then the key limitation there was there had to be at least 2 years of overlap with Phenocam imagery for us to use the site or to have enough data to justify kind of doing an analysis for a given site. And in the Southeast, we looked pretty hard to find sites that would fit that description, but for whatever reason, we couldn't find any sites that met our requirements. So it wasn't because we were completely ignoring the Southeast, it's just none of the sites currently were able to provide the data needed for the analysis. But I would expect in these humid ecosystems for precip to have less of an impact overall than greenness or some energy variables like GDD. So.
I think there was two other questions. One, when you showed the path analysis results, are all the path connections significant in the path analysis? Because some of the path arrows had very small values, or is it's like every arrow gets a value?
Right, so those are like the coefficient values comparable to a linear regression. So my guess is some of those much smaller values are not significant, and you can look at the partial relationship plots and see that there's almost no relationship. Given that's a time series analysis, I didn't really focus too much on the significance levels because there's so much autocorrelation. I was just looking for more general patterns and strengths of these correlations among different sites.
I think one more question here. Yeah, so there was a question about if LAI would have been a better factor to explain evaporative fractions, since LAI integrates both phenology and amount of leaf or greenness.
Yeah, that's a question I've gotten a lot in this work. And the reason we chose to go with greenness instead of maybe a measure of LAI is because we wanted to consider other ecosystems like in coniferous forests, where you're not going to have a large turnover in needles every year. So there's not a large change in leaf area, but you do see strong seasonal patterns in both greenness or plant physiological activity and water fluxes. So we were more interested, I guess, in what the leaves were actually doing rather than when the leaves come on the trees. But certainly in some ecosystems, changes in leaf area are going to be maybe a better predictor than just greenness itself.
Thanks. Yeah, so Ryan, thanks for your talk. I think it's I talk for myself, but from a flux
Thank
power
you.
perspective, it's always good to see new things, and I haven't seen mixing diagrams used a lot at flux tower sites, and that probably is related somehow to the lack of instrumentation or observations that we need for that. So one question here is, what kind of instrumentation do we need to estimate or measure advective fluxes in the boundary layer? Like, for example, at a Ameriflex tower.
Yeah, so the way that they were doing this, I'll actually link the paper in the chat, but it was one of my co-authors on the paper that we're currently drafting. And basically they used a network of Doppler LiDARs and ARES in order to derive advection from using Green's theorem. So you need several different ARES and Doppler LiDARs co-located with one another, and then they need to be spaced out like, I can't remember what the ideal spacing is, but usually you want to have 3 or 4 so you can kind of create this polygon in order to derive advection. But again, I'll link the paper because they probably explain it a lot better than I do. And they talk about some of, the ideal setups in terms of how many instruments you need and spacing between them.
Perhaps a follow-up from, like, because we heard about the windsong data, would it, like, I mean, it's manual work, so I guess all these like radars and continuous observations are much better suited for that. But would it be possible to get advection also from just doing the same with like launching 3 or 4 radiosondes around the tower to get information about that?
Yeah, we were just saying that too, I think, and that's where it would be cool to compare these measurements, like to collaborate. Let's do this.
Yeah, that would be really interesting.
Yeah.
Especially, I guess, in the boundary layer where you maybe wouldn't have them drifting too far, I guess, initially. So that would be really interesting.
Mm-hmm.
I think you could do that.
Yeah, especially if you launch several at the same time.
Definitely.
Yeah, I think during a previous IOP at SGP, this is Yunyan. Can you hear me? Yeah, at SGP side, that I think people have been experimenting launching different at different locations, but with the same time. But also in addition to what Ryann just described, that at both SGP and it's going to be at the Southeast US, we are going to have this triangular setup of the RE system together with Doppler LiDAR. And so the spacing is about 30 kilometers, I guess. There is a paper, this Ryann just mentioned, by Tim Wagner and Dave Turner on this. And so there is an optimal spacing to derive the advective tendencies. And so we are going to have this, we already have this at SGP, and we are going to have this capability at Southeast US, the coming field campaign next year. Yeah.
That's cool.
Yeah, thank you for elaborating on that.
Other question here for Ryann, one more. So there, like, if we do not correct for energy balance non-closure for the eddy covariance method, do we risk biasing our entrainment flux estimates?
So could you possibly maybe rephrase that a little bit? Because I'm not exactly sure.
Yeah, so I think it's, so usually like the energy balance at the flux tower sites is often not close, and usually it's about 80%. So, and we don't know where the remaining 20% are lacking. So the question would be, if we would underestimate the surface fluxes by 20%, would that directly lead to a bias in the entrainment flux estimates because it's calculated as a residual?
Yeah, absolutely. Sorry, for some reason my brain didn't quite comprehend what was being asked. Yeah, so that's actually kind of what we're trying to account for when we're doing these uncertainties. It's not really necessarily, I guess, showing the bias in terms of our, approach here. We're just kind of showing plus or minus, 1 standard deviation, but it would definitely introduce a bias that would maybe cause us to overestimate the role of entrainment fluxes if we're kind of underestimating our surface fluxes.
So then there are a few more questions also for Yunyan, and there's one for Ryann and Yunyan. So Can we include precipitation in the mixing diagram? Because I think Yunyan showed it for clear sky days. So is it possible for rainy days too?
I'll start and then I would love to hear more input. Basically, we've kind of talked about this. I think it would be a little bit difficult because you're getting phase changes in here. This has kind of been just a subject of debate within my own little group. And I don't know if we know exactly how to do that well yet, or even how to approach that problem, but I would love to hear someone else's opinion.
Thank you, Ryan, for starting to answering this. I think it really depends on, right? So if you have this heavy precipitating event, especially with the significant subcloud layer evaporation of precipitation, it actually changed the energy budget. And we, right now, from observation, we do not have a strategy how to evaluate that. But from models, it definitely you can characterize that. So if it is for that perspective, mixing diagram often apply to conserve the variables, and this extra term actually changed the conservation of the theta and the Q total, right? So I think in that situation, you probably won't use it, especially for PBL and subcloud layer budget, because there is additional a non-adiabatic process there. So that's my answer, especially for the heavy precipitation. But I like to echo what Ryan is saying, that if it's for drizzle or other cases, I'm not sure. But drizzle evaporation cooling is also not that insignificant. Usually it's also very significant too. So that should be, I don't know. Yeah. Yeah.
Yeah, we've talked about trying to incorporate this and looking at like marine stratogenetics and stuff, and it's just, it becomes really complicated really fast.
Yeah, exactly.
Yeah, I see that Yunyan already responded to some of them. I think there was one you answered. There's one question about if you use direct flux observations from grasslands and forests for your model simulations that you showed.
We didn't directly use that yet, but our LES study is based on the difference between winter wheat and grassland. But the original setup, especially the difference between the forest and grassland, the peak sensible heat flux is about 100 watts per meter square. So I think we haven't driven this, and the the latent heat fluxes difference is minor. It's about 50 or less. So yeah, we haven't tried the difference between these two yet, but we tried the winter wheat and grassland. Yeah.
And I guess to wrap up, perhaps we have one more minute here. What kind of instrument would be most useful to be deployed at a range of Ameriflex sites for most cloud interaction studies? I mean, obviously it depends on the study, but like if you could choose one or two.
Sure, I think I would think the one that can accurately characterize cloud base and cloud fraction. I think
so
in
oscillometer
that,
or something like that?
Yeah, I think so. And I think Doppler LiDAR can also do that too. And also at the same time, Doppler LiDAR provides the vertical velocity measurement. Yeah. A
bit more expensive though.
Yeah, I know. Yeah, but it's also more advanced in characterizing TKE, the vertical component.
Definitely.
Yeah.
And hopefully these things will get cheaper over time. So.
Hope so.
Okay, I think we hit half of the hour. So thanks to all the presenters for sharing your research with us today. And yeah, I hope you will join the Ameriflex webinar series for the upcoming events. I think there are a few more coming up in the Year of Water. And yeah, I hope to see you soon.
Thank you.
Thank you so much.
Thank you for organizing this. Thanks.
Yeah,
Yes, thank you.
Bye-bye.
Bye.